Hello, everyone. Welcome back to the AAS YouTube channel. And this is more of the good stuff. This is the AAS Journal Author Series. And I'm super happy to have Haolan Tang with us today. Hey, Haolan.
Hi, how are you?
I'm doing great. What's your geolocation?
Oh, I'm right now in Los Angeles in my own office.
Ooh, you're in your office. Wow.
Yeah.
Okay. Wow.
Yeah.
So they're letting you
working. How's that working here?
So they're letting you in. They're letting you in the building. That's pretty good.
Yeah, wow. Actually, although my paper is about like a theory, actually I'm the experimental people. So I need to come here every day.
Okay. Awesome. Very cool. Let's see. So I'm in Arizona.
Great place.
Got any questions about Arizona? Do you have any questions about Arizona? We have hummingbirds.
Yes. Do you like hummingbirds?
Hummingbirds are great. I have a lot in my yard. Well, we have a fair amount of vegetation for living in the desert. You know, a lot of hummingbirds. Yeah. Basically year round. There's like a month or so in January where I think they go and hibernate or something. But
yeah. Actually, January is their kind of the reproduction season. So you can see lots of babies.
Cool.
Babies, nests. Oh, that's pretty cute. That's pretty cute.
Very nice. Very cool.
We can have another conversation about hummingbirds. I can give you 1 hour. Okay.
We should do absolutely. We should do hummingbirds. We should talk about hummingbirds on the moon. We should talk about hummingbirds in planetary systems. Yeah, it would be great.
Yeah. Definitely.
But at least I'm not necessarily an expert on that topic, but and maybe hummingbirds are something you do for research, but what do you like to do for research, Haolan?
Actually, so I already mentioned that I'm actually the experimental people. So I mainly investigate the different kind of isotopic system in different extraterrestrial targets, like meteorites, like for example, like meteorites from the moon, meteorites from the early solar system, to try to study the early events when the solar system, during the solar system formation, and then during the evolution of the system, or right after the moon formation. So this is mainly what I'm studying right now. And this paper actually is my first paper to only write the paper only based on the calculation, only based on the theory. So you made a good choice. Thank you.
Well, it is a really lovely paper. I love it. I picked it out. And so speaking of, so let's go ahead and take a look at this really lovely paper. And you have been warned, people, it's going to be maybe a little theory heavy. And so we have evaporation from the lunar magma ocean was not the mechanism for fractionation of the moon's moderately volatile elements. And Haolan, take us away.
Yeah, actually, so first of all, let me just give you like a brief introduction of the background story of the whole paper. So the motivation for this paper, and of course for a whole of the projects that Ed Young and me right now are doing, is that so in 2017, Hing and O published a paper on Nature. So in that paper, actually, they proposed that for all the early planetary bodies. So actually, his target element was magnesium. So he proposed that the magnesium silicon isotopic fractionation actually occurred near equilibrium for all the planetary objects in the early solar system.
Okay.
But actually, before that, people always think that, oh, let's imagine that we have the early solar system, right? And basically the pressure, of course, will be pretty low. So if you just like evaporate some kind of it should evaporate very fast, right? It should evaporate very fast. So therefore we can observe both the loss of the elements and the isotopic fractionation. So you can just imagine that, for example, if you heat up some kind of water, and the water was boiled, right? So the light material will escape the faster rather than the heavier one. Sure. So we should observe some kind of the heavy isotopic fractionation inside of the remaining melt, remaining planetary objects. So, and we thought this effect can be big, but actually he proposed that, okay, there should be near equilibrium. So we shouldn't observe like big isotopic fractionation. And then that triggered our study about like evaporation during the experiment and also like in theory. So we want to study the evaporation overall from the magma ocean, the widespread magma ocean in different kind of the planetary objects. And then we want to know, okay, what is the condition, what truly happened during the evaporation from the widespread magma ocean. So that is all the background, like the background motivation for our study. Cool. And then at Young, the second author of this paper, he published the paper, I think that in last year in Icarus. And then he also do some kind of like the theoretical calculation and on the magnesium and the silicon. And basically his target is a small early formed planetary body that was a radius of around like 700 kilometers. And then in the early solar system. And then he of course derived a lot of equations. He said, okay, so basically we should expect the near equilibrium fractionation for magnesium and for silicon. But both, of course, is a major element, right? Yep. Magnesium, silicon, oxygen, iron in our Earth or other kind of planetary object. Yep. And then I feel like, oh, this project is very interesting. So how about the moon, right? The moon actually formed very different from other early formed planetary bodies, right? First of all, we know the characters of the Earth-Moon system is very special, right? We have first of all, we observed the moon as we had observed the basaltic crust, right? So we know the moon was formed from kind of rapid cooling. It must have cooled very fast. And then we observed a very small iron core. And we observed the isotopic similarity for all major elements. For example, oxygen, very similar to the Earth. Yep. Magnesium, silicon, titanium. Titanium is very refractory. So like extra refractory elements. So here, let me just say that what is refractory elements? It means that, think about it's just like a very high temperature vapor. And then the temperature goes down. The very first condensed elements include the titanium. Yep. So titanium is very hard to be vaporized. But titanium, on the other hand, is the excellent tracer to trace the origin of different planetary bodies. For example, the titanium isotopic composition on the Earth is different from, let's say, the Mars or from other meteorites. So we know that titanium is kind of the good tracer for the reservoir for different kind of the planetary bodies. But the moon shared a similar titanium isotopic composition with the Earth. So in this case, of course, this is like a long time ago, maybe we already know that for decades, right? The moon was formed through the moon forming giant impact. That is that we have the Mars-sized impact on the Earth, and then we generate the moon. So in this case, I think in 2015, Wang and Jacobson, 2016, Wang and Jacobson observed the isotopic differences on the moderately volatile elements. I mean, different from the major elements. Moderate from the isotopic differences on the moderately volatile elements between the Earth and the Moon. So this is potassium. So moderately volatile elements is like the condensation temperature is like ranges from 700 Kelvin to 1200 Kelvin, like potassium, like zinc, like rubidium. Okay. So this actually triggered the debates, like long-term debates in this field. So this isotopic fractionation must imply something like during the moon formation, right? So this isotopic fractionation it may trigger during the impact. It may yield it during the moon formation, right before the moon formation. So think about it, we have the impact, right? And then we will have a melt disk around the Earth. And then the moon was formed inside of the melt disk. It may occur as a topic fractionation inside of this melt disk. Okay. Or when the moon formed, of course, the surface of the moon was very hot because, of course, there's a lot of like tons of energy, right? Still remains on the moon. And then we have the lunar magma ocean. And of course, there will be the evaporation, there will be the gas escape.
Yes.
During the evaporation of the lunar magma ocean, the cooling of the lunar magma ocean. Then in this at this period, we may also have isotopic fractionation. So right now we have like 3 different mechanisms that could explain this isotopic signal. So giant impact itself, or melt disk, or lunar magma ocean evaporation. So this paper actually we try to focus on the last stage, try to investigate with the restriction of the time and temperature, whether this mechanism can explain the isotopic fractionation of the moderate volatile elements signature.
Cool. I'm with you. Cool.
And you have seen the conclusion from the title.
Great. You know what's coming.
Okay. So this is the kind of the brief introduction about the background story of our motivation, and also the background story of the moon, the isotopic signature of the moon. So I think I can go through the papers section by section, right?
If you like, yes.
Yeah. So first of all, I want to give a brief introduction about the word saturation. So this is the section 2. So this is for section 2. We try to kind of introduce the conception saturation and try to introduce how can we kind of like simulate the condensation, evaporation, or equilibrium fractionation. So here we introduce the conception saturation. So for saturation, we can understand, like, for example, if we have, let's say, the water, like the water evaporation, right? We have a liquid water and a water vapor. If in the atmosphere we achieve the saturation is equal to 1, which means that the two-phase vapor and melt achieve the equilibrium.
Yeah.
So the rate between the vapor go into the water, the water phase, or the liquid phase go into the vapor, the rate is the same. So in this case, we reach the saturation is equal to 1. So similarly, we can also just assume that, okay, we can calculate the isotopic fractionation factor when the S is equal to 1 for potassium. Here, I just take potassium as an example to simulate the isotopic fractionation during the lunar magma ocean evaporation. So we can calculate the isotopic fractionation during the equilibrium fractionation between the melt and the vapor, which is the equation 2. So so for the equation 2, you can see, so the beta is a reduced factor of, here I just take example of the microcline. This is the potassium bearing mineral. I just take it as an example for calculation. And then the beta for for vapor, actually we can treat it as a 1. So the beta gas is equal to 1. So actually the alpha potassium equilibrium for the microcline versus the vapor, we can calculate it based on the equation 2, depending on the vapor temperature or the system temperature. So let's just assume that the temperature is equal to like 1800 Kelvin. We can calculate the alpha, the isotopic differences, and it's only like 0.04 or something. You can just calculate it based on the equation 2. And actually 0.04 is too small to explain our observed isotopic differences between Earth and Moon, which is 0.4 per mil. So it's like by a factor of 10. So actually, by the section 2.1, I just want to rule out that the equilibrium fractionation between the vapor and melt cannot explain the isotopic signature observed from the lunar sample.
Okay, I'm with you.
So, and here I didn't discuss about the condensation, which is the S is larger than 1. So that is the vapor is oversaturated. So the vapor condensed back to the melt. Right. I didn't discuss it in this paper, but actually overall, just give you the conclusion. Overall, this condensation is going to generate identical or negative isotopic composition in the melt compared to the vapor.
Yep.
So obviously, we have the heavier isotopic compositions. Of course, we cannot explain it by the condensation. So of course, the last one is evaporation, right? So evaporation, it means that S is less than 1. So it ranges from 0 to 1, which is, I think, is section 2.2.
Yep.
So for section 2.2, so the equation 3 is just the Hertz-Nielsen equation. And equation 3, actually, this is the basis of our derivation. Okay. So here we, the J is just a flux of the evaporative flux. And net means that, okay, if we have the surrounding pressure, of course, the presence of pressure will give the negative feedback of the flux, right? So think about it. If we have a vacuum surrounding, we don't have any background pressure. So of course, the evaporation will occur very fast, right? It just, it continuously evaporate, continuously transfer the liquid phase to the vapor phase. So the flux is going to be very fast, very rapid. In this case, the S is equal to 0. Saturation is equal to 0. However, if we have a little bit kind of the background pressure, then the surrounding of the pressure will suppress the flux, the evaporation flux, right? So we're gonna decrease the evaporative flux. So this is the point of the equation 3.
I'm good. Yep.
Yeah, and then from the equation 3, so this is just the basis of the equation 3. So to apply the equation 3 to our case, the moon-sized body, we have to consider about the effect from the time, the evaporation time, and the size of the moon. Why? Because let's think about that. If we have a contour-sized body, which means that only like 1 centimeter size body, and we want to evaporate it. Even if the surrounding pressure is like, for example, 1 bar, we still have a rapidly fast evaporation. Why? Because the size body is very small relative to the mean free path of the vapor molecule. So which means that, okay, we have a molecule or we have atom like evaporated from the surface of this small body. And then the mean free path is much longer rather than the size of the body, which means that it have like large chance to escape from the parent body, from the evaporated body.
Yes.
Right? So which means that even if the surrounding pressures is kind of high, let's say 1 bar, 0.1 bar, it's still like highly possible for a vapor to escape from the evaporated body. On the other hand, let's think about the moon. Moon is so big, right? So compared to the evaporated molecule, evaporated like species, like vapor. So which means that, okay, we have the vapor, like vapor species come from the melt. And even a little bit, only a low pressure, background pressure, like background molecule, like pressure, the mean free path cannot be longer than the size of the body.
Yes.
So of course, it's gonna knock the encountered the surrounding molecule and then go back to the melt.
Sure. Okay.
Right. So this is actually this explained. This is reflected in the equation 4.
Yep.
So in equation 4, you can see that so the net flux is also relate on. So here in the denominator, we have an S, and S is the size of the evaporated body, and the D is a diffusivity, and diffusivity is calculated based on surrounding pressure.
Yep.
So, and then here, based on the equation 4, of course, I won't do the derivation, and you can see the derivation in the appendix 1, and then we can calculate the flux for the light isotope and the heavy isotope, and then we can achieve the equation 7, the complicated equation. And then in the equation 7, this is the isotopic fractionation for like a certain system based on the evaporative duration, the body size, and the surrounding pressure. And actually, let's go to the figure 1.
Okay.
Here, yes.
Here we go.
So figure 1, like 1A, just to show you the flux or the saturation associated with a different kind of evaporation time. So, and with a different size, also with a different size. And here I just take example of 500 kilometer, 1,000 kilometer, and also moon size.
Yep.
And of course, the gamma, 2 gamma is just the evaporation, the parameter. So it's determined from different kind of lab work. So we don't need to worry about that. In a certain temperature, here is 1800 Kelvin, and with a fixed background pressure. So we can see that it just at the very beginning, so still the figure 1, at the very beginning, the saturation, okay, so here, the y-axis is the ratio between the J net and the J evap. J evap means the flux during the free evaporation.
Okay.
Okay, so which means that when the ratio is approaching to 1, which means that the J net is approaching to the J evap.
Yep.
So that means that the saturation is approaching to 0. On the other hand, okay, when the ratio is approaching to 0, which means that the net flux is decreased dramatically. So of course, it achieves the saturation is equal to 1 anyway. So cool. Here we can see that for like large size body, like 500 kilometer, even like 1,000 kilometer moon size, at the very beginning, the saturation is already kind of very close to 1. Right? Here it already start from like 0.02 or 0.005 at the very beginning, right? And then it decreased with the time. So here, figure 1, just to show you the effect from evaporative time scale. But overall, you can see that for the body up to like hundreds of kilometers as a radius, overall the saturation is like approaching to 1, or like the net flux is much smaller rather than the free evaporation flux. And then the figure 2 is more critical in our study.
And figure.
Oh no, sorry. Figure B. Sorry, figure 1.
Figure B. 1B.
Figure B. Yes.
Yeah. Sorry.
So figure B, actually this figure reflects the equation 7, and here I just plot the isotopic fractionation in the net evaporation on the moon-sized body with different surrounding pressure with a certain temperature, which is equal to 1800 Kelvin.
Okay.
And here I plot both the alpha for potassium and also the alpha for rubidium.
Yep.
So you can see that when the pressure is very low, it's like 10 to the minus 15 bar, we can achieve the free evaporation. We can achieve the free evaporation alpha. And then when we increase the background pressure, we can see the alpha increase dramatically and then approach to the equilibrium fractionation factor. And then when the pressure is like 10 to the minus 9 or larger than 10 to the minus 9 on the moon, we should expect the near equilibrium fractionation during the evaporation. Right? You can see the plateau, right?
Yeah, yeah.
After like when the pressure is larger than 10 to the minus 9 bar. So overall for the moon, it's very easy to achieve the near equilibrium fractionation during the evaporation. Overall, this is the motivation of the session 2. So which means that the pressure is the most critical parameters to simulate the evaporation of the lunar magma ocean. And then how can we simulate the pressure? We need to build up the rock vapor atmosphere above the lunar magma ocean. And which is session 3.
Yep, the rock vapor.
Okay, so in the session 3, actually here we discussed this issue based on like into like different aspects of the atmosphere. So 3.1 here we are discussing about the vapor composition due to the magma ocean evaporation. And here, so we can use the thermodynamic calculation. So basically, we can calculate the different kind of Gibbs free energy in different species. For example, magnesium, MgO, evaporated to magnesium plus oxygen, or potassium oxide evaporated to potassium plus oxygen. We can just calculate different kind of Gibbs free energy corresponding to different temperature and then the different oxygen fugacity. Then we will know the different partial pressure of the species in the vapor. So basically, this is the basis of this calculation. So overall, for the conclusion, for the bulk composition of the moon, we know that for like 1800 Kelvin, the predominant species of the vapor is sodium, oxygen, and potassium.
Okay.
Overall. And maybe a little bit iron. So this is what we discussed in the 3.1. And then in 3.2, there's another issue that we have to consider. So in 3.2, the main motivation for 3.2 is that, okay, what is the phase of the atmosphere? In another word, whether this atmosphere is dry or wet. This is actually very important because it's just it can determine the structure of the atmosphere. So here, dry means there's no phase change in the vapor. So think about our atmosphere.
Okay.
At a certain altitude, the water vapor achieves the saturation. Then we have a cloud, we have a rain. And then this is kind of similar to the moon.
That's right. I'm with you.
Right? So especially for the moon, like the saturation pressure for sodium and potassium, of course, is much higher rather than the vapors, rather than the water vapor. So we have to consider about when with increasing altitude, along with the atmosphere, we need to consider about the pressure change, the temperature change, and then whether we will have a phase change inside of the atmosphere.
Yep. Yep.
So overall, what we can do is that we can directly go to the figure 2. So I think figure 2 is very straightforward. Yes. Okay. So here in figure 2, just schematically show you two types of the atmosphere. So we can say like the root 1, 2, and 3, it show you like the white atmosphere. Yes. So figure A show you the relationship between the temperature and the pressure, and figure B show you the pressure versus the entropy.
Mm-hmm.
Okay. So and the solid black line is the saturation of the sodium oxide between the liquid and the vapor, the gas. Okay, so if we have the higher pressure on the ground, okay, right above the melt, let's say, for example, 10 to minus 3 bar or 10 to minus 2 bar.
Okay.
Yes, and then at the beginning, we will have the adiabatic convective atmosphere. So that's also like how to say that, like a troposphere on the Earth, right? So we will have well-mixed convective atmosphere. And then in this layer, which is the root 1, the gas will just adiabatically convective until it reach the saturation pressure. So that is until it just meet the saturation line of the sodium oxide, and then the sodium can condense from the vapor. So in root 2, the temperature and pressure will follow the root 2 and actually follow the saturation pressure, and then until it reach the equilibrium temperature of this planet, so which is the root 3. So from root 3, the atmosphere will go back to kind of the vapor phase, and then it's just we reach the exothermal layer. So this is the kind of a white atmosphere. And then for the dry atmosphere, we don't have this kind of complicated phase change. We just say, oh, we have the convective troposphere, and then we reach the equilibrium temperature, or we just reach the stratosphere, in which we don't have any kind of convection. The heat will just irradiate to the space. Yep. So that is root 4 and 5. So for the dry atmosphere, it's just the gas. There's no condensates.
Yes.
So of course, for the dry atmosphere, of course, it starts from the lower pressure. So overall, this is kind of the two types of the atmosphere. Then right now we need to determine that, okay, which way we want to go in, right? So here, the pressure of the rock vapor atmosphere, okay, first of all, it determined from the vapor evaporated from the melt, right? So that is the input. But we also have an output, right? We have gas escape. Yep. Right? So we have some kind of this like the pathway of the gas, right? We have an input and we have an output. So if we have strong output, so of course the pressure inside our atmosphere is going to be lower. Yes. Right? We have like strong flux, of the gas escape. We will have maybe have a dry atmosphere. If we have a lower gas escape, we may have a wet atmosphere. So this issue about the rock vapor atmosphere actually lead to the next issue. So what is the mechanism of the gas escape for the rock vapor on the moon? And here I think yes. So this is 3.2.3. Okay, so here we discussed about the mechanism of the atmospheric escape from the melting moon. And here we major focus on the hydrodynamic escape. And hydrodynamic escape is like, you can treat the gas as a fluid. So which means that the gas gonna escape as like the entire fluid and removed from the planet. So which means that it only occurs in a collisional gas. So when the pressure is high enough, the gas molecule, it has like, of course, a collisional with each other.
Yeah.
So of course we can treat it as a fluid, not like the individual gas molecule. So of course it can remove from the planetary atmosphere entirely.
Yes.
So this is we call the hydrodynamic escape.
Mm-hmm.
So we think since our pressure, we treat the pressure like 10 to the minus 7, it's still pretty high. It's still high enough to treat the gas as a fluid. So it's first of all, we considered the hydrodynamic escape. And then for hydrodynamic escape, we already know how to calculate where is the boundary of the atmosphere, so-called the transonic point, which is the equation 16. This is the boundary, we treat it as the boundary of the atmosphere. And we also know how to calculate the hydrodynamic flux. So I think that is the equation.
No, here you're getting into atmosphere.
Oh, the equation 22. Okay, anyway, this is the equation 22.
Nonlinear is good, 22, there you go.
Yeah. Yes. So here, in the section 3.2.3, we made an assumption and tried to get some kind of starting point to calculate or to determine the surrounding gas pressure. So here, first of all, we assume that, okay, the background pressure is around 10 to the minus 7 bar. And then within this pressure, within this pressure, we can calculate the evaporative flux on the moon. And then we build up the atmosphere structure based on like static atmosphere and based on like hydrodynamic wind. So hydrodynamic wind, this is kind of new conception in this paper, in our chatting. So hydrodynamic wind means that actually it doesn't mean that the hydrodynamic escape only occurred beyond the transonic point, but the hydrodynamic escape can actually affect down to the atmosphere. It can fill up the pressure in the atmosphere. So that's why in the figure 3, you can see that for the static atmosphere, the pressure decreases faster in the high altitude. Whereas if we have a hydrodynamic wind, the pressure decreases much slowly rather than the static atmosphere. Basically, I can just explain it, like simply explain that in this way. So overall, we can calculate the evaporative flux based on the surrounding pressure is equal to 10 to the minus 7. And then we can calculate the escape flux in this background pressure. And then we can see, okay, whether we achieve the steady state. And we found that even with such a low pressure, the evaporative flux from the lunar magma ocean is smaller than the evaporative flux, than the escape flux. So which means that the gas escaped faster rather than it come out from the vapor, from the lunar magma ocean.
Okay.
So which means that even with such a lower pressure, we still didn't get the enough input into the atmosphere. So we need even lower pressure to achieve the equilibrium, achieve the steady state.
Yes.
So overall, we made this test, and like because this 10 to the minus 7, we already achieved like a dry atmosphere. So even like a lower pressure, we only considered about the dry atmosphere. We don't need to consider about the wet atmosphere. We don't need to consider about the phase change, all these complicated processes. So we just play kind of the trick game to escape the wet atmosphere, and then we only discuss about the dry atmosphere, and then we only discuss about kind of the lower the surrounding pressure.
Right. That's simple. So
okay, so this is the motivation of the whole part 3.2 until 3.2.3. Okay, and then in 3.2.4, here it comes a new issue. What about the influence of the Earth?
Yeah.
Okay. This is a complicated paper, I must say.
We'll go on, keep going. That's fine. It's perfectly
okay.
I'm with you.
Okay, so here, we just consider about, when we consider about the boundary of the atmosphere, we firstly consider about transonic point, which has been given in the paper in the previous session. And then, like one of our colleagues suggests me to consider about the heliosphere, the moon's heliosphere relative to the Earth, which is the equation 23.
Yes.
So at the beginning, she suggests me to kind of compare these two boundary to determine what is the boundary of the atmosphere. And then we found that, okay, we shouldn't determine the boundary such easy, because the molecule evaporated from the moon, it has a force both from the moon and from the Earth, the gravity force, both from the Earth and from the moon. Especially at that moment, the Earth and moon, the distance is very short, only 5% to 10% of the present distance. So in this case, we had to consider about the gravity and the rotation of in the Earth-Moon system. So to do this, actually here, it is reflected from equation 27.
So let me make sure I'm following this. So the physical point is that the Hill radius pushes the sonic point inward toward.
Yes, basically.
That's what I want to get. Okay.
Yeah.
Now I understand it. I understand.
So basically, we can use a kind of equation 27. So this is the equation of the gravitational acceleration at the point R, like located between the Earth and Moon.
That's right.
And then we can say, okay, it has both the force from both the Moon and the Earth. And overall, we can solve this equation, and then we can get the result as the figure 4. So,
right.
So in figure 4, the x-axis is the Earth-Moon distance. The y-axis is the ratio between the critical radius and the transonic point, when we assume the Moon is independent, no force of the Earth.
Yeah. Okay.
Right?
Yep.
So you can see that when the Earth-Moon is shorter, it's like 20,000 kilometers, the ratio is close to like 0.6.
Yes.
Which means that actually the critical point, the new transonic point, is push inward to the Moon.
Yes.
Which means that actually the Earth can strengthen the gas escape from the Moon.
Okay.
And also, it can also the detailed result can be shown in the figure 5. So in figure 5, it's kind of similar to figure 4, but I just made a contour of the altitude of a critical the critical point corresponding to the Earth-Moon distance and the temperature of the vapor. So basically, if you say, okay, if I have, for example, the Earth-Moon's distance is around like 30,000 kilometers and like 1800 Kelvin, and then the altitude of the critical point is around 1100 Kelvin above the ground of the moon. Okay, and this is the new boundary of the atmosphere in this temperature with this Earth-Moon distance.
Yes.
Okay, so now, okay, it seems that we clean up all the issues related to our project. So right now we know, okay, how to calculate the evaporative flux. We know how to calculate the escape flux, and we know where is the boundary of the atmosphere.
Right.
Now we can finally determine what is the pressure right above the Earth, the lunar magma ocean. Okay, which is the section 3.2.5, the steady state atmosphere.
Bingo.
Okay, so here, as shown in the figure 6. Okay, so in the figure 6, here we calculate the intergradient flux. So intergradient flux, it means that the flux, the J times the total area, the surface area. So that is like the total the evaporative how to say that the evaporation rate for the certain surface area.
Yes.
Okay.
Yes.
So in this figure, the x-axis is the background pressure and the y-axis integrating the flux. And the 3 black solid line is the integrated evaporative flux corresponding to different temperature. 2000 Kelvin, 1900 Kelvin, 1800 Kelvin.
Okay.
And then the gray bar and the red bar are the escape flux beyond the critical point in the steady atmosphere and with the hydrodynamic wind.
Yes.
Okay, so basically we just focus on the hydrodynamic wind, and you can see the crossover point. Yes. The crossover point between the gray bar, the red bar, and the 3 solid line determined the background pressure in the steady state atmosphere. That is the pressure when the input from the lunar magma ocean is equal to the output from the gas escape.
Yes.
So in this case, we achieve the steady state in the atmosphere. And this pressure is around 10 to minus 8.
Correct. Yep.
Okay, now finally we know how can we determine the pressure during the lunar magma ocean evaporation. And this pressure is around like 10 to minus 8, like at least a 10 to minus 8. It could be higher when we have a higher pressure, higher temperature. And 10 to minus 8, to be honest, if we go back to the figure 1b.
Okay. Figure 1b.
Okay. See, so figure 1b,
right here.
Yes. So the 10 to minus 8.
Right.
With 10 to minus 8, we still have the near equilibrium evaporation fractionation factor.
Correct. Yep.
So.
Yep.
Okay. So it seems that the evaporation of the lunar magma ocean also cannot explain the isotopic signature of the MVE in the moon, the moderately volatile elements in the moon.
Okay.
Then in the last, I think in the section 4. Okay. Then in section 4, we just think about it a little bit more. Feel like, okay, the evaporation cannot explain the isotopic signature, but what if we have the vapor melt exchange, the isotopic exchange? What if the vapor was isotopically fractionated inside of the atmosphere? Then we may still have the fractionated vapor down to the ground and then exchange with the melt because of the diffusion. At the beginning, we thought, oh, because of the diffusion, right? Because like if you say like the heavier isotope, of course the diffusivity, it's gonna diffuse slowly rather than the light one because of the gravity, right? So we considered a little bit more about this. Then we said, okay, first of all, because the gas, when it escaped hydrodynamically from the planet, it behaved as a fluid. So we won't expect any isotopic fractionation during the escape, just because it just removed entirely, right? So there's no chemical fraction, there's no isotopic fractionation during the escape. And then inside of the atmosphere, it seems to me that at the beginning, it seems to me that, okay, maybe the gravitational settling can cause the isotopic fractionation along with the altitude because of the gravity.
Yes.
And then it's actually, this is one of the reviewer reminds me, I really want to thank him here.
Or her.
Her, yes. And
we don't know.
They actually, he or she mentioned that, okay, the hydrodynamic escape are not only affect on the boundary of the atmosphere, it also affect down to the deep into the atmosphere. So actually what you need to do is that you have to compare the velocity of the gas molecule inside of the atmosphere.
Yeah.
And there are kind of 3 different velocity for the gas molecule inside the atmosphere. One is the velocity yielded by the hydrodynamic wind, or called the Parker wind inside of in the paper. The other one is the gravity, also called the terminal velocity. It is determined by the mass, the gravity, and also the temperature. And then the third one is the diffusion. That is caused by the pressure gradient.
Right.
So if the hydrodynamic wind, the velocity of the hydrodynamic wind dominant the total velocity, which means that actually the hydrodynamic wind can homogenize the whole atmosphere. So in this case, we won't have any isotopic fractionation or chemical fraction inside of the atmosphere. So basically, it's just a competition among different velocity. And this is shown in the equation 31. Yes. So the equation 31 with actually it is shown for like the total flux for like the species I, and then the first term, the equation 32. Sorry, okay. It's equation 32.
Sure, diffusion.
So the first term of the right hand side is like to reflect the hydrodynamic wind flux, and the second term is reflect the flux due to the diffusion. And the third term is determined by the terminal velocity. So that is the gravity and also the temperature of the gas, the species itself. So basically we can solve this equation based on like a different, corresponding to different altitude, corresponding to different the pressure inside of the atmosphere. And then the result overall is shown in the figure 9. Okay, so the figure 9 actually, the x-axis W over U. W is the terminal velocity. So overall determined by the gravity and the temperature of the gas. And U is the velocity yielded by the hydrodynamic wind.
Yes.
And the y-axis is the ratio. It's just reflected by the altitude. It's just reflected by the showing the altitude. So it's an altitude divided by the critical point. So basically, y-axis just to show you the relative altitude. So here we calculate difference, in the different condition. For example, like 400 Kelvin or like 1550 Kelvin, the gas temperature. And then like 10% or 100% show you the Earth-Moon distance. So 10% means that the Earth-Moon distance is like 10% of the present distance, and 100% is like the present distance.
Yeah. Okay.
And here, actually, you can see that actually overall the velocity yielded from hydrodynamic winds overall is just dominant the whole velocity, the total velocity, right? It's like from 10 to the minus 4 to 10 to the minus 2.
Right.
So overall, the hydrodynamic wind is very strong in our case, especially when the temperature is very high. Here it's like 1550 Kelvin, and the Earth-Moon distance is kind of short. So actually, which means that the shortened Earth-Moon distance as well as the high temperature can strengthen the effect of the hydrodynamic wind. Okay, so based on this figure 9, then we can calculate the isotopic fractionation and the chemical fraction inside of the atmosphere, which is the figure 10. Okay, here is a figure 10. Okay, figure 10a show you the potassium isotopic fractionation associated with the relative altitude, and figure B show you the ratio between the potassium and the sodium associated with the relative altitude. So two dashed lines. One is the low temperature with a closer Earth-Moon system, and the other one is just like a higher temperature. But overall, you can see there's no isotopic fractionation or the chemical fraction because of the strong hydrodynamic wind.
Yeah, right.
We may have some isotopic fractionation here in the solid line, 400 Kelvin with the present Earth-Moon distance. In this case, the hydrodynamic wind is not too strong, so we can still preserve the isotopic fractionation or chemical fraction due to the gravity or diffusion. But overall, this is not a realistic situation in our case. So overall, from the lunar magma ocean evaporation and the mechanism of the gas escape, right now we can conclude that overall the lunar magma ocean evaporation cannot be the mechanism to explain the MVE isotopic signature in the moon. So overall, we think, or we propose, this isotopic signature required other kind of mechanism, for example, some kind of mechanism inside of the melt disk right after giant impact as an explanation. So overall, this is our conclusion. Our conclusion is kind of a negative conclusion. We just ruled out the last stage, the lunar magma ocean evaporation, as a mechanism for the isotopic signature of the MVE for the bulk moon.
Ruling out a scenario is important.
Thank you.
Well, if you've got 3 options and you
Yeah, at least
when it doesn't work, well, okay, that's great. That's 1/3 of the problem.
At least we show them, okay, the shoulder's closed. Take a detour.
So I wanna understand a little bit the blue line in this curve.
Mm-hmm.
So basically,
Yeah.
if at 10%, it's basically evolving adiabatically.
Oh, okay. So we did actually, there's a little bit more story about this. Actually, this paper, it took us like 2 years to publish this paper just because we have like different kind of review from different reviewers. And one of the comments from the reviewers is that, okay, because here we just assume our atmosphere is the pressure is very low.
Yeah.
So we already calculate the energy balance. So we already proved that, okay, the energy emit from the lunar magma ocean is much larger than the gas absorption inside of the atmosphere.
Okay.
So which means that for our atmosphere, the gas can maintain the constant temperature. So like 1500, like 1800 Kelvin. This is because like the energy emit from lunar magma ocean is big enough to maintain the energy.
Yeah.
In the gas.
It's a dominant energy reservoir.
Yeah, but some of the planetary scientists, they suggest me, they give me the comments that, okay, you still need to consider about, for example, what if the gas is like adiabatically expanded? How in this case, you also need to consider about this case. So in this case, the gas temperature actually changed inside of the atmosphere. And of course, the critical point will also change with the temperature. But actually, so here, the 1550 Kelvin adiabatic, it's implied this case. But overall, we didn't see any like isotopic fractionation also in this case. We didn't plot the 1550 Kelvin like 10% or 100% in this plot just because it's all the same.
Yeah. Okay, got it.
But overall, the code for the adiabatic expansion gas, overall, I must say we still need to improve the code because, yeah, it's not easy to calculate. We still need to improve our code to adopt the atmosphere with a little bit higher pressure.
Okay.
Yeah.
Very good. Cool. Are we good?
Yeah. Do you have any other question, or I know maybe I presented like too specific. I hope I can make it simple.
Yeah, no, I followed it. It was fine. It's pretty awesome that you were able to eliminate evaporation as a driver of the fractionation. That's pretty cool. So you mentioned that now that one scenario is eliminated and you had a somewhat lengthy review process, what are the next steps? Where do we go over the next 5 years? Are there new calculations to do? You mentioned improving the adiabatic code. There might be other ones. Are there other observations that could be done? Just sort of look in your crystal ball and where do we go?
Okay, so right now we are doing the evaporation experiment. So in the lab. So actually we are designing, so there's a kind of a little object and we have the gas flow and we want to observe the saturation with different kind of gas flow. So actually this we call the levitation system. So this experiment actually simulates the evaporation inside of the early solar system in the early form of the planetary bodies.
Laboratory astrophysics.
Yeah. So this is the ongoing project that we want to do right now. But I also know that actually this paper is not the end of the world. This is the end of the work for the end of the project for this study, not the end of the world. The end of the world. Actually, there's a still kind of debate related on this this model or related on this mechanism. The whole mechanism is still kind of debatable. So I really want to say in this here is that of course we got all other kind of valuable comments from our reviewers, and one of the comments is very good, and I know that they're also working on a pretty similar project, and I hope they can also publish their work pretty soon. So their question is that, so here remember we build up our model based on the steady state atmosphere. So their question is that whether we truly have the steady state atmosphere on the lunar magma ocean.
Right.
So here our debate or our controversial point is that, so here we assume that the hydrodynamic wind only affect in a certain level inside of atmosphere, but they feel like, okay, what if the hydrodynamic wind could affect the down to the ground right above the lunar magma ocean? So in this case, maybe we don't have any steady state. Maybe the gas may escape much faster. But even right now, we don't have the answer about that.
Okay.
I want to see that, because I really think this is very interesting. And this, if they want to simulate this process, it's super complicated. It's very complicated because overall, for the cosmochemist, we study the evaporation inside of the lab. So in the lab, all the situation is very ideal, right? So we may have a vacuum furnace, or we may just have like certain pressure. We do the evaporation. But actually, for the evaporation on the planetary bodies, the main thing is that it's hard to determine the boundary between the evaporated body and the background pressure. So this is very, the boundary problem is even right now is pretty hard to address. So we can also work on the theory, I mean, like in the future, but mainly we're gonna focus on the lab work.
Cool.
Yeah.
Very cool. Awesome paper. Haolan, thank you so much for spending some time and walking us through it.
Thank you. Thank you for your invitation.
My pleasure. My pleasure. All right, everyone. Thank you so much, and we will see you on the next one. Bye-bye.
Bye.